So I'm going to talk about surrogates in the context of deep learning. The talk will be based on some works with two of my students, Yonatan Fiat and Eran Malach, as well as with a friend of mine, Jonathan Wexler from Oregon. So I will start with some motivation as why do we need surrogates. The motivation is from practice use of deep learning. So what's wrong with deep learning? Everyone hears about how great is deep learning, and indeed it led to state-of-the-art in various domains. But there are many, many problems with deep learning. The first problem is that sometimes it fails, and when it fails, you don't really know what to do because we don't really understand how to fix it. Sometimes we think deep learning works, but it actually doesn't. And sometimes it does do something that looks okay, but it's not quite what we think it should do. In some sense of, it doesn't find the explanation that we as humans would like it to find. And there are many, many more problems, and one nice summary of them is a work by Gary Marcus. So let me elaborate about the problems. As a professor in the university or as a manager in Mobileye, one of the sentences that I hear the most is, I've tried X, but it didn't work. And X can be deep learning or any other thing. I must say that this is the most uninformative sentence that one can hear. It has nothing to do with reality because you don't know why it didn't work. Maybe it's because the one that tried it is not competent enough. Maybe it shouldn't work. You have no idea. So it's really zero information. But if you understand X, you can find out what went wrong. You can ask the student, OK, did you do this or that? And then you can understand what went wrong. But if you don't have a clue how X works, then you have a problem. And this is what happens in deep learning. Sometimes we think that deep learning works, but it doesn't. So here is a quote from Eric Schmidt. And he told it to me personally, but then I found that it's also in interviews all along the internet. So he told me over dinner that computer vision is a solved problem, which is nice to know. But then these are some images from Google Photos, and they are automatically labeled by the solution, the solved problem, yes, the best solution of Google. And indeed, you see scrapers and airplanes and cars and bikes and gorillas. Oops. And the guy that was tagged as a gorilla wasn't very, very happy about it. So it shows that even though you think that you are, even in a relatively well-defined problem like ImageNet, where you have a predefined set of classes and you need to classify them, still the deep learning solution sometimes does funny things, or maybe they are not funny. But it's even worse than that. Even if it seems to work, it doesn't find the simplest explanation. And as a motivation, I was interested lately in solving word mass problems because my daughter is at 7th grade and she's learning to solve these problems. And they said, it would be interesting to think how a machine learning can learn to solve these problems. So simple things like there are 3 eggs in each box. How many eggs are in 2 boxes? Okay. So let's see. You know what? Let's start with a much simpler problem. How much is 3 by 2? Okay. Can we teach a deep network to tell us how much is 3 by 2? Well, we're making deep learning drive autonomous cars, right? So how much 3 by 2? Should be an easy task. Okay, so I generated examples. I will elaborate how exactly I generated them, but here you see the multiplication table. So it's just for the visualization 1 to 5, but I trained it 1 to 10. And you see the ground truth in the yellow, white rows, and the predictions of deep networks after training in yellow, and it seems very, very good. Okay, so it learned the examples that I gave it. But what about the other examples? Okay, so now these are out-of-sample examples, and as you can see, 2 by 2 is not 4, it's 21, according to the deep network. This is strange, because it knows that 2 by 1 is 2, and 2 by 3 is also 11. So even though it knows many, many things about this multiplication table, and it's not a question of extrapolation, it's all interpolation, okay? It's things that come from the same distribution. It's not distribution drift. It's not domain adaptation. Something very, very simple, and it's very, very strange, okay? So in order to figure out what's going on, this is still not an explanation, but it describes a problem in more detail. So here you see one row of the multiplication table as a graph. For example, here you have 3 times a number, okay? So the blue line is the correct answer, and the red line is what the deep networks learned, okay? And I would guess that if I will show you only the blue points, okay? If I will show only the blue points and will ask you to generalize, none of you will come out with this picture, right? You will find something completely different. You will fit it to a line, right? But this is what the deep networks did. So maybe I cheated in order to show that I did not. I will explain that I even made the problem easier for the neural network. So how to multiply 2 numbers? Maybe you need a deep network for that, okay? But I represented the inputs as binary sequences, as binary numbers, okay? So the first number is sum of I, AI, 2 to the I, where AI is either 0 or 1, okay? So we need just 4 bits, okay? So the input to this network is just 8 bits. The first 4 bits is for the first number. The last 4 bits is for the second number. And by a very, very simple calculation, you can see that we can express this function of multiplication by a one hidden layer ReLU network. So there is no problem of expressivity here. And it's actually a very, very simple one hidden layer network. So the right solution is just to have n square neurons. Here n is 4. So we just need 16 neurons, okay? And each one has weights of 1 on I, 1 on the J's place, and -1 for the bias, and all the rest is zeros. So it's really very, very simple thing. So there is a good solution in the network. So even though a simple solution exists, SGD learns a completely different solution that also fits the data. Yeah? There was no fitting problem. There was an overfitting problem. So all of this story comes to tell you what, in my opinion, is the role of theory here. What we miss is a theoretical understanding of what's really going on in deep networks. The first thing that I would like to emphasize is that we don't really understand the inductive bias that neural networks uses. What is exactly the inductive bias? We see that in the multiplication table, the neural network uses some inductive bias, which is very different from what we see as a simple explanation in the Occam meaning. So in the same way, neural network would not replace Newton to find that F equals M times A. Okay, no chance, because it will not find this solution. It will find something else. How does the inductive bias depend on the architecture of the network, the initialization of the network, the optimization algorithms that we are using? Regarding generalization, the famous paper by Zhang et al. About understanding deep learning require rethinking generalization. We don't really understand good enough the generalization in deep networks. And of course, the major problem of optimization, when and how gradient-based optimization works. So these are the basic questions, and we really don't understand them. And just to show you that, that unlike other things in machine learning, in neural networks, the inductive bias is not just a function of the hypothesis class that we use. It is also a function of the initialization schemes that we are using and of the specific algorithms that we're using. So here's an informal version of a theorem from a paper by myself, Ohad Shamir, and Shaked Shama. So you can fix some architecture of a neural network. And then the theorem tells you that for any initialization scheme of a neural network, so you decide on the initialization scheme for the weights. And this initialization scheme induces an order over the set of functions that can be expressible by the same architecture. So I'm only talking about things that can be expressed by the architecture. And gradient-based optimization is blind to almost all functions according to this order. So it can only learn the first function in the order, but all the tail of the order. Gradient descent cannot find these solutions. So it means that there are many, many things that we can express with a neural network. Most of them, gradient-based algorithm will never find. So gradient, the optimization algorithm itself induces an inductive bias on what we are going to learn. As I showed in this equation here, a feed-forward ReLU network can solve the problem at hand very, very easily. It's expressible by one hidden layer ReLU network. So there is no problem of you need a deeper network or you need a different operations in the network. No, here is a calculation. It's really solvable by one hidden layer network. Okay, so since we do not understand a lot about deep learning, the plan of attack that I propose in this talk, and this is the title of the talk, is to use surrogates. So instead of studying deep learning, let's study something else. And you can think about two types of surrogates. One type of surrogates is build simpler models. And this will be the first part of the talk. So you want to build something simpler than a deep ReLU network that behaves similarly to deep learning on specific tasks, but is easier to analyze theoretically. And then we would like to reflect on the behavior of deep learning and gaining insight on questions like inductive bias and generalization and potential failure points of deep learning from these simpler models. Of course, we're not expecting that simpler models will be as good as neural networks on all tasks. But if they are similar to deep learning on some specific task, maybe we can get a lot of insight from it. The second thing the second type of surrogate that you can think about is simpler distributions. So we know that in the worst case, if I'm allowed to choose a distribution, then neural networks cannot work, cannot learn. But in practice, on some real data sets, they are actually working very, very good. So there is a family of distribution on which neural networks work and on which neural networks do not work. So if we can come up with distributions for which we understand what's really going on, maybe, again, we can get insight. So the two parts of the talk will be about a surrogate model in which we separate gating from linearity, and the second part will be on surrogate distributions. So after this very, very long introduction, let's go for the first topic, separating gating from linearity. So as you all probably know, a rectified linear unit is a function of x parameterized by a weight vector w. I neglect here the bias for simplicity, but basically the function is maximum between x transpose times w and 0. But we can also rewrite it as a multiplication of two terms. The first term here is a gate. It's just a 0-1 function telling you that the value of the gate is open if the inner product is greater than 0, and the gate is closed if the inner product is smaller than 0. And the gate is multiplied by a linear function w transpose times x. Once we write it like this, we can think maybe we can separate the gate from the linear function. And this is exactly what a gated linear unit does. So it is parameterized now by two vectors, u and w. One is responsible for the gate, the other one for the linear function. And apart from this, it looks exactly the same as a ReLU neuron. So up until now, it's not very different. Of course, everything that you can express by a ReLU network, you can also express by a GaLU network, because you can simply set u to equal w. And then you are back into a ReLU network, right? So we didn't lose anything in expressivity when we moved to this representation. But what do we gain and how do we optimize? Before I will answer it, let's go back to these images of the multiplication table. And since our goal is to have a surrogate model, I would like to convince you that we are behaving similarly to ReLU networks with GaLU networks. And indeed, it seems the resemblance is striking. So you see, again, the same thing. We trained on the same examples a ReLU network and the GaLU network, and I will explain how we train GaLU network soon. And quantitatively, it's of course not the same numbers, but qualitatively it looks exactly the same. Okay? So maybe it's interesting to study this model. Another example of how similar is GaLU to ReLU is when we apply them to some standard data sets. So here are results on the MNIST data set and on fashion MNIST data set. What you see is a loss function as a function of the number of neurons, and it looks pretty similar. I also depict here another line, which is linear networks. In linear networks, there is no nonlinearity at all. You just train a linear function, but a deep linear function. Okay, and as expected, you get a straight line because you don't get anything from depth. It's still interesting to study linear networks as a surrogate model. But what you can see here is that this surrogate does not really capture similar performance to ReLU networks as opposed to the GaLU networks, which looks really much similar to ReLU networks. Okay, so hope this is convincing enough that this model makes sense, at least as a surrogate. Now let's think about what we can tell about this problem. So the first issue is the issue of optimization. Can we train GaLU networks? We need to tune two parameters, the gates parameters, the u vector, and the weights of the linear function parameters, the w vectors. The gates are untrainable with SGD because the gate function is just a step function. The gradient is always 0. And this is a good thing because we're going to keep them at the initialization, and this will make our life very, very simple in terms of analysis. So in GaLU networks, we're just initializing the gates and then forget about them. Okay? So we only train the linear part. Okay? What's nice about this is that once we keep the gates fixed, we can train the linear part provably. Okay? We don't need to rely on luck. We can have an algorithm that provably converges to the solution. Why? It's a simple exercise to take a two-layer network. So the description here is for a single output, one hidden layer network. And what we do is we push the parameters from the second letter into the first. And we can do this because everything is linear once the gates are fixed. So we get just the parameters of the first layer, and then we get that the prediction is just linear prediction, but examples are filtered by the gates. Okay? So we can solve it exactly. When we're talking about more than a single output, it's more tricky, because then the problem is equivalent to a problem of minimizing a convex objective, but with low rank constraints. There are many, many known approximations for this problem, but empirically what we found is that the low rank constraint is not really important, as it behaves the same with or without the low rank constraint, so let's just forget about it, okay? So if we forget about the low rank constraints, we actually all the time have a provably correct algorithm to train the linear weights. Okay, so in terms of optimization, we're much better than ReLU networks. We know exactly what's going on. What about expressivity? Because we do not train the filters, seemingly we lose in expressivity. So, of course, it's not difficult to find cases in which we lose, but we're not trying to compete with ReLU networks. We're trying to get some insight on ReLU networks. So let's see when we do not lose for ReLU networks. So the question is, what can be expressed by a GaLU network, assuming that the filters, the U vectors, are fixed to their initialization? So in expressivity, it depends on the problem. But one very, very natural way to measure model capacity is to see how good it is in overfitting. Okay? How good is it in memorizing labels? Okay? So can we memorize a random sample? And here we have exact characterization of how good GaLU networks can memorize random labels. So assuming that we have m random examples, and we look at GaLU networks with k neurons, and let d be the input dimension, then the expected loss of the solution of the GaLU network, which is, we can talk about the minimum because we know to solve it exactly, is exactly 1 minus the rank of some matrix over m. This matrix is simply repetitions of the data, but every example in each repetition is filtered by the corresponding gate. Okay? So it's sort of a random matrix because the gates are defined by random vectors. And the rank of this matrix behaves very, very closely to a full rank, meaning that this rank of x bar is k times d. So what we see here is that GaLU networks are actually almost optimal in terms of their ability to memorize samples. Why? Because the optimal thing that you can have is something that will reduce error as a function of the number of parameters. Here the number of parameters is exactly k times d, and we get exactly the behaviors that we want. So this is very nice, and it actually behaves exactly like this in practice. And if we compare GaLU to ReLU for task of memorization, we see that they are almost the same. Okay? There are differences, but they are very, very, very similar. Okay, so if this is an interesting model, what can we say about it? Unfortunately, we can say about it much less than I want to be able to say about it, but I view it as a point for further research. What we do have to say about it is that GaLU networks are, in a sense, optimal for data sets which are highly clustered piecewise linear distributions. So, and if you think about what ReLU networks are doing intuitively, this is exactly also when ReLU networks are good. So you partition the space, okay, and you hope that in every partition there is a linear function, or approximately there is a linear function that explains your data. So for GaLU, we can show that this is indeed the case, but the result is not very, very strong because we need pretty heavy conditions on the highly clustered data set. Anyway, this is a start, and I believe it's an interesting direction to continue studies is GaLU networks. It's, of course, much easier than to study ReLU networks, and I think they exhibit several phenomena which are very, very similar to what's going on in ReLU networks. They can also tell us something about generalization. So I will mention again this paper by Zhang et al. About understanding deep learning requires rethinking generalization. And in that paper, the starting point is this bound here, which looks like almost all the bounds that we have in learning theory. We say that the generalization error of some hypothesis is smaller than the training error plus something that looks like a capacity measure of the hypothesis class divided by the number of examples to some power. The P can be 1 or 2. Okay? This is a typical behavior of a generalization bound. So what Zhang et al. Showed is that if you run SGD on exactly the same network architecture, meaning that the hypothesis class remains the same, okay? Exactly the same number of examples. So this term here looks exactly the same. But once you run it on the true labels and once you run it on the on completely random labels, then on the true labels it generalizes, and on random labels, of course, it does not generalize, but it fits the data very, very well. So the term here is 0 in both cases, okay? But the term here is in 1/2 if it's a completely random label, or close to 0 if it's true label. This means that any bound of this form cannot explain what's going on in neural network. And this is an observation in the paper by Zhang et al. Okay? So the first thing to ask is, do we see the same in GaLU network? And we actually see exactly the same thing in GaLU networks. So what you see here in the graph, you see the accuracy as a function of how much label noise we put in the data, where if we put 1/2 label noise means that we are fitting random labels, okay? And 0 label noise meaning that we're fitting the true label. And what we see, the optimal thing is this line here, okay? And both ReLU and GaLU do something like this, okay? So again, they look very much like the same thing. Now, can we gain something from GaLU in order to understand what's going on in terms of generalization? And when you think about it, GaLU networks are very similar to simple vanilla linear regression. And if you think about the phenomena that is described in Zhang et al. Paper, it is not surprising at all when you think about linear regression. Maybe the surprising thing is that all learning theory does not think about linear regression. This is more surprising, okay? But what's going on in linear regression? When you do linear regression, if I have d examples in d dimensions and 0 noise, I'm going to fit the data perfectly and generalize perfectly, because this is exactly the degrees of freedom that I need in order to learn the exact true model if there is zero noise. Okay? Of course, if there is a lot of noise, then according to learning theory, I need d over epsilon examples in order to learn up to level of epsilon. Okay? And actually, this was formalized better by a paper of Rosset and Tibshirani that show that the sample complexity is roughly sigma square d over epsilon, where sigma is the standard deviation of the noise. So what we see here, exactly what Zhang et al. Saw in their experiment in a neural network. They saw that if there is no noise, then you don't need a lot of examples. With the same hypothesis class, nothing was changed. Same hypothesis class, you don't need a lot of examples. But if you inject noise, you need a lot of examples, or in other words, you overfit. Okay? So this already holds in vanilla linear regression. So again, what we learn here from GaLU is that a lot of what's going on in neural network is basically a random partition of the space and then linear regression. Okay? So while neural networks look fancy, they are not doing much more than that. Okay. So this was part 2. I have maybe 5 minutes, right? More or less. Okay. So part 3, I would like to talk a little bit about surrogate distributions. So again, we know that in the worst case, deep learning cannot work. On the other hand, in practice, on some real data sets, deep learning works pretty good. So we want to understand what's going on real data. But since modeling real data is hard, let's search for surrogate distributions. So what is a good surrogate distribution? The ultimate objective is to identify the set of distribution for which deep learning works. Okay? This is the ultimate thing one can do. And there is just one problem with this ultimate objective. It's too hard. Nobody can even think about how to start tackling this problem. Okay, so let's be more modest and try to identify a set of distributions which contains some real distributions and for which deep learning provably works. This is still too hard. Okay. Nobody could even come close to it. Okay? So what I propose is something much more modest. We would like to identify a set of distributions which is not interesting by itself at all. It doesn't necessarily contain any interesting real distribution. But maybe it will give us insight on when and how deep learning works. Okay? So again, it will not help you in any way but getting insight. Okay? So I'm going to show you 2 such distributions. Both of them are not interesting by itself. Okay? But they give a lot of insight on what's going on in deep learning. The first one is a deep generative model for synthetic images, where we generate images starting with a label. We generate a small-scale image where each pixel represents a semantic class. For example, we put some sky, some grass, and stuff like that. Okay? Then we build more images in a hierarchical manner, where each time we take one semantic pixel and we construct out of it a new semantic patch. Okay? Again, it is semantic, but it captures more fine details of the distribution. So here is an illustration. We start with just, say, 3 types of semantic pixels, which are corners or straight lines. Then we generate more and more fine details, and at the end we can generate some synthetic images of digits. Okay? Now, I'm not claiming that this is how images are generated. I'm not claiming that this distribution is of any interest. It's just a model that maybe will be able to tell us interesting things about deep learning. So we indeed studied this distribution, and we found a rather surprising property for this distribution with respect to SGD algorithm. So informally, what we found out is that if you train a two-layer convolutional net on some intermediate level description of this model, okay? Not something which is very close to the label, okay? You train a two-layer network. The objective is predicting the label, which is far after a lot of building of more and more and more fine images. You are just looking at some coarse image. So of course you cannot predict the label very, very good, but at least you can predict something about the label, but this is not interesting. The interesting thing is that SGD finds automatically the next level in the hierarchy. So in a sense, it finds the latent structure according to this model without any intention to do it. And I think this is an interesting property that may hold to some extent on real data as well. As a side effect, it enables layer-by-layer reconstruction of the latent features. So for this synthetic model, we are able to prove that if you are doing layer-by-layer learning, where each time you learn 2 layers and throw the last one, which is something that is also done in practice in many cases, then you provably converge to the optimal model. All right, so last topic, depth efficiency in fractals. So depth efficiency is a basic question. Every time we are hearing about deep learning, deep networks, and a natural question, do we really need this depth? Okay? And there are many recent results showing depth efficiency, showing that there exist functions which can be expressed by a small deep network if it is deep, but if you are using a shallow network, you need exponentially large in terms of width network. But my concern about all of these results is that even though such functions exist, it doesn't mean that SGD actually can find them. And in order to tackle this question, we looked at fractal distributions. These are distributions that are defined by some affine functions that apply again and again in a recursive manner on themselves. So it's interesting to compare fractals to deep networks because you can have a very, very similar relationship between the depth of the fractal and the depth of the network. So what we showed is that, first, this intuition is correct, and indeed there is depth separation on fractals. So a network of depths O of n, where n is the depth of the fractal, can express the fractal, but a shallow network requires exponential width. So depth separation exists for this fractal distribution. But we wanted to see if SGD can learn these functions, even though there is a method for expressing them, it doesn't mean that SGD can actually learn them. So in order to do this, we looked at the approximation curve. The approximation curve is a curve that's telling you, you know that you need a deep network, but maybe you gain something for using a shallow network. So how much you gain from using a shallow network? How much of the error you can explain by a shallow network? And what we show is that if there is strong depth separation, meaning that if you cannot express anything in shallow network, only in deep network, then SGD cannot learn them as well. You can only use depth if there is approximation also by shallow. And this goes side by side with results that we know in practice. I never saw a case in which shallow network did nothing, was close to 1/2 in terms of performance, and deep network was very, very good. It's never the case. It's always the case that shallow network does something, and the deeper you go, you get better and better. So we give a formal explanation, and I see that Chaim is standing here, meaning that I'm out of time. So I will go directly to the summary. We lack a good understanding of basic properties of deep learning, in particular, how to control the inductive bias. If I want to learn the multiplication table, how do I tell the network that I want smooth solution? Okay? We currently don't have a methodology for inducing or for forcing the network to go to a certain inductive bias or to a certain direction. We don't understand good enough how the inductive bias depends on the initialization and optimization algorithm. And I'm in pursuit after good surrogates. Thank you very much.